My name is Isabel. I am a tutor at TuteSmart and welcome to the ATAR Notes January lectures. So if you're watching this, you're probably here to get a little more info on HSC chemistry. So that's what we'll be doing today. I will be taking you through HSC chemistry. Hopefully by the end of this 2 hours you would have learned something. So this should be fun. Okay, cool. So as you probably already know, since you are here, ATAR Notes is where we are, and there's a bunch of cool stuff. So if you ever think about needing anything extra, we are the place to go. But not here for an ad, you're here for HSC chemistry. So again, my name is Isabel, and I'll be taking you through this lecture. Here are some fun facts about me. So I graduated in 2022. So I just finished my first year of uni. I'm going, in January in next year, 2024, I'll be studying medical science. I actually changed degrees. So I started off as a Bachelor of Applied Science, exercise physiology, and now I'm here. So yeah, I'm transferring to medical science, which is cool, but that's not really what you need to know. I did 3-unit maths, English advanced, chem bio, modern, and I got a band 6 in all of them. So I was an all-rounder. I got an ATAR of 99.3, and I don't know why I put modern history was my best exam in the HSC there, but that's just a fun fact. And some other fun facts that aren't school related. I enjoy playing touch, dancing, going to the beach, doing water sports, and all that kind of stuff. Summer is my favorite season, so very excited. Been at the beach a couple of times this week, so yeah, love the beach, love the water. And when you guys are watching this in January, I'm recording it in December, but when you're watching it in January, I will actually be island hopping in the Philippines. So when you have the live chat going on the side, that's not me. That is somebody else. I'm having fun in another country, but I'm still here, like, digitally teaching you guys about chemistry. But yeah, so here is the game plan for today. We're doing a little intro and overview, then a module 5 refresher, little crash course, making sure that you don't forget anything that you learned in module 5 last year. And then we're going to go through module 6. So module 6 only has 3 inquiry questions, but it's got a lot of stuff packed in there. So we're going to go through all of that. And then at the end, I'll do my little talk on how to study, how to take care of yourself, how to survive the HSC. If you're going to listen to anything today, that's probably the part to listen to, because the HSC can be stressful, and I want to tell you how to make it the least stressful possible. Back to the questions thing. So there's a live chat going on, right, like next to my head somewhere on the side. And with that live chat, just ask questions. I won't be the one answering them, but there will be another tutor on there who will be ready to answer any of your questions. And from experience, as someone who went through HSC chemistry, I know how hard it can be. So no question is a silly question. It's like, if you have any question, just pop them into the live chat and you'll probably get an answer, or you'll definitely get an answer. It's our job to give you answers. But yeah, don't feel silly if you don't understand something. Everyone learns in different ways. If I'm just talking at you through the screen with a slide that might not make sense to you, you might not learn that way. So if you're confused and have a question, ask, and maybe I'll explain, like maybe the other person will explain it in another way. But yeah, to get the most out of this lecture, since it isn't me in person, using the live chat will be really, really helpful. So don't be afraid to do that. Okay, cool. So we're going to do our little module 5 refresh now. Module 5 is equilibrium. Got a lot in there as well. It's quite jam-packed. But as a little overview, we have first inquiry question on static and dynamic equilibrium. Second is on factors that affect equilibrium. That's when we talk about LCP. Le Chatelier's principle. Then we have inquiry question number 3, calculating the equilibrium constant, and solution equilibria. Those last 2 inquiry questions are quite calculation based, especially with the HSC. So yeah, be mindful of that. So in terms of like general things to remember with equilibrium, reactions that have a forward and a reverse, those reversible reactions, they can exist at a state of dynamic equilibrium where the rate of the forward reaction is equal to the rate of the reverse reaction. And that's what we talk about in the first inquiry question. Then we have LCP, and then we have our calculations. So, as a little refresh question, here it says equilibrium constant is 50 at 500 degrees Celsius. So remember, with equilibrium constants, it is the equilibrium constant at a certain temperature, because the only thing that can change the actual value of an equilibrium constant is temperature. No matter how much you add to the vessel, change the pressure, whatever, that doesn't change the equilibrium constant numerically. It will just shift and restate itself at that ratio. What changes the value of K numerically is temperature. So that's why it's really specific that it's 50 at 500 degrees Celsius. Then it asks how many moles are present at equilibrium. So what you need to do is you need to write out the equilibrium constant expression for this system. So it's products over reactants. So you'd have hydrogen iodide, hydroiodic acid, if you will, Hi squared, because there's a 2 in front, and then you have on the bottom, so like that's on the top, on the bottom you have the concentration of hydrogen gas multiplied by the concentration of iodine. Then you sub in, like, let's say X, you sub in, X for like Hi, and then the 0.1, and then you go for it. You solve it mathematically, and then you get an answer, 0.7 moles. Keep in mind that you need to be aware of units when it comes to this stuff, so you want to make sure that you're always working in moles, moles per liter, like big M. You don't want to be working in just moles, because if the vessel is like 5 liters in volume, then you'll have a very different concentration as the number of moles. But yeah, it's a side note. So if we go on to some theory stuff as a refresh, also if you see me looking like, this is so not related to module 5, but if you see me looking like upwards, it's because the monitor with all of the stuff is like bigger up there. So like the camera's down here, but like the monitor's up there. Anyway, that's moving on. So some definition stuff that you need to know. Static and dynamic equilibrium. Static is when the rate of forward equals reverse, and that rate is 0. So this is for irreversible reactions where it's gone to completion. That is static equilibrium. Dynamic is when the rate of forward equals the rate of reverse, so that's the equilibrium part. But this rate is greater than 0, so the reactions are still happening. They just don't look like anything's happening because it's happening only at a microscopic level with particles changing and that kind of stuff. So yeah. Then you have open versus closed systems. It's a really common question to be asked about open and closed systems because it's so important to establishing dynamic equilibrium, having a closed system. Open system means that there's a transfer of matter and energy. So if you think of a beaker, just an open beaker, if you have water in there, the water can evaporate and escape as gas into the atmosphere. Same thing, like the atmosphere can come into the water and dissolve. So that's a transfer of matter, and then it can also transfer energy. Closed system, if you think of something with a lid on it, like a test tube with a plug, that can't transfer matter. The water in the test tube can't be evaporated out. So it can only transfer energy, not matter. Isolated systems, nothing can transfer. It's just on its own. Kind of hard to get those, but they do exist because there's a definition for them. Something that usually gets overlooked when we talk about Module 5, mainly because you learn it in Module 4, so you don't go over it that much in Year 12, is entropy and enthalpy. So you need to know your exothermic and your endothermic reactions. Exothermic reaction, we have energy being released. Endothermic reaction, we have energy being absorbed. So that's what those graphs show. You have the activation energy being smaller in exothermic reactions and larger in endothermic reactions. You can just look at the graph and see how potential energy changes with the reaction progression. So exothermic and endothermic, they relate to enthalpy. It relates to the heat content of the system. Entropy is something that relates to the chaos and disorder. So the more disorder there is, the higher the entropy. If you think about your states of matter, you have solids which live really close packed together. Very close. They can't move around much in a solid. That is a very ordered system, so that has low entropy. If you have gases, you have the particles buzzing around everywhere. They can move freely. They can do whatever they want. That is high entropy because there's lots of chaos and lots of disorder. So that's entropy and enthalpy. The next kind of thing in Module 5 before you go on to LCP, and sometimes you get questions that relate collision theory with LCP, but collision theory is about what is actually happening in reactions and what causes them to occur. And what causes them to occur are these collisions between particles. And in order to have a successful reaction, you need to have 3 different criteria met. So the first is having the particles actually hit each other. So you can't have hydrogen gas and iodine gas combining to make HI if those hydrogen and iodine aren't crossing over at all. If they're separate, there's no way that they can react. They have to actually hit each other for something to happen. So first thing they need, actual collisions. Next thing is activation energy. They need to reach a certain amount of energy. And once they reach that amount of energy, they can react. But if they don't reach it, they don't react successfully. It must be enough to break bonds that are holding the original reactants together in the first place. So it needs to be enough energy to break those bonds to form the new bonds. And then you have molecular orientation. This just means that they have to collide at the correct angle. You can't just have them collide anywhere. They have to collide at a specific angle for it to work. So if you think about it, that's a lot of things that need to go right for a reaction to occur. And in chemistry, you see a lot of reactions, and apparently all of this is happening every single time you see one of those reactions. It has to be very specific angle, very specific amount of energy, and then actual collisions. So when you talk about collision theory, most of the time you're using it to explain how could we increase rate of reaction or how could we decrease rate of reaction. So that's something to consider. Inquiry question 2 is about factors that affect equilibrium, and this is basically all LCP stuff, Le Chatelier's principle. Le Chatelier, very famous. You should know this definition like the back of your hand when it comes to the HSC, because LCP is everywhere, and you need to be able to recite the definition of LCP on the spot if you need. So LCP is if you have a system at dynamic equilibrium and that system is disturbed, what would happen is the system will minimize that change. So it will minimize the disturbance, try to counteract it, and then establish a new equilibrium. So we need to think about that to figure out what happens when certain disturbances occur, which way it shifts, all that stuff. That's all LCP, and that's all this second inquiry question. So with concentration, this is like I think this is the easiest one to wrap your head around. But if you have this reaction here, A plus B makes C plus D. If you add B, you're increasing the concentration on the left-hand side, on the reactant side. So you have too many reactants, and the system wants to counteract that change. So since you have too many reactants, what you want to do is use up those reactants so it goes back down to a normal amount. And by using up all those reactants, you end up making more products. You end up having a higher rate of reaction for the forward reaction compared to the reverse because you're using up more of the reactants. So that's why if you increase B or A, you'll increase the forward reaction rate, which is called a shift to the right. If you increase C or D, you're increasing the amount of products. You have too many products, it increases, you want to get rid of it because LCP is all about minimizing change. You want to counteract the increase in C and D. So how do you do that? You use up C and D. So you've increased C and D, you use it up. How do you use it up? By the backward reaction. You do the reverse reaction, and by doing the reverse reaction, you get rid of C and D and you increase A and B. So that's that. Same thing can be said about removing. So if you remove A or B, that's pretty much the exact same as increasing C or D. So if you remove A or B, you're decreasing that side. You're decreasing A and B. And to counteract that decrease in A and B, you want to increase it. So you want to do the opposite of removing. You want to add. So how you do that is you increase the rate of the backward reaction to fill it up again. And same thing with the removal of C or D. So you just got to think of like what's the opposite of the disturbance, and then how can I make that opposite of the disturbance happen. So if we're removing something, the removal is the disturbance. We want to do the opposite of that disturbance. So we want to add. How do we add? By favoring that reaction. So hopefully that's all good. Okay, then pressure. So pressure is something that applies to mostly gases. You'll get gas questions. Yeah, almost always gas. Never seen pressure with anything else because you can't really do pressure with anything else. But it's also related to volume. So Boyle's law is a law that is in like, I guess, physics, it's just a law of the world, Boyle's law, and it's that pressure and volume are inversely proportional. So if you increase pressure, you decrease volume. If you decrease volume, you increase pressure. If you increase volume, so if you make something bigger, you decrease the pressure. So I like to think of all changes in pressure in terms of volume, just because it's easier for me to wrap my head around, but everyone thinks of things differently. So for me, we have this reaction, we have the Haber process being shown, so nitrogen and hydrogen being turned into ammonia, and what's happening is, let's say we have an increase in the volume. If we have an increase in the volume, if it's in an inverse proportional relationship between volume and pressure, increase in volume means a decrease in pressure. A decrease in pressure is what's occurring here. So first step in figuring out what the shift is looking at the molar ratio. So you compare the left with the right. On the left we have 4 moles, so 3 plus 1, and then on the right we have 2 moles, just from the 2 ammonia. Then I like to think of it in terms of the volume, as I said. So if I'm increasing the volume, I have lots more space to work with, and I want to fill up that space. So I go to the side that produces more moles, because I want to fill up the space. It's quicker than going to the side with less moles, because it won't fill up the space as much as the more moles side. So I'd go and favor whichever reaction produces the most amount of moles. In this case, it's the side with 4. I want to make 4 moles of gas. So I'd be favoring the reverse reaction. It will shift left. This will mean that there will be an increase in concentration of nitrogen and hydrogen, but a decrease in concentration of ammonia. So if it was the opposite way around, I skipped too quickly. If it was the opposite way around, if we decreased the volume, I'd want to go to the side with the least amount of moles because I have a smaller space. I don't want to be occupying all that space. It'll be too cramped. So I want to favor the side that is less cramped, which is the 2 mole side. So I would favor the forward reaction then. Or you can just, I like to think of it in terms of how much space they take up. But you can also just think of it as if you increase pressure, you want to go to the least amount of side, least moles, decrease pressure, more moles side. Yeah, but I just like to think of it in terms of volume. Then finally, another thing that can influence LCP is temperature. So we have to consider whether something is endothermic or exothermic before we figure out which way it shifts. So if we have a forward reaction that's endothermic, what would happen is if we increase temperature, the temperature increase has an increase in the rate of reaction for both forward and reverse. That's the first thing that would happen, because just if you increase temperature, more particles have enough activation energy to collide, more collisions happen, greater rate of reaction. So that's the first thing that happens. But then there's a shift in equilibrium. And what happens is the endothermic reaction, let's say the endothermic reaction is the forward one. We know that endothermic reactions absorb heat. So if we heat it up, we have all this excess heat. What are we going to do with all this energy, all this excess heat? It wants to be absorbed by the endothermic reaction. So when temperature increases, the endothermic reaction is favored. So if it's an endothermic forward reaction, it'll shift right. If it's an exothermic forward reaction, so let's say, it's an exothermic forward reaction. What would happen is if you increase the temperature, you have all this excess heat. What are you going to do with it? You want to absorb it. You want to get rid of that excess heat, because that's the opposite of adding heat. You remember LCP is about counteracting all that stuff. So if I have too much heat, I counteract it by adding if you have too much heat, you counteract it by absorbing. And you absorb heat through endothermic reactions. Since a forward reaction would be exothermic, you would favor the reverse, which would be endothermic. And then that would shift left. So you need to figure out whether the forward reaction is endothermic or exothermic before you can make a decision about which shift it is. But overall rule is if there's an increase in temperature, it will favor the endothermic. A decrease in temperature will favor the exothermic. Another thing is catalysts. So adding a catalyst decreases the activation energy. And this is just something that increases the rate of reaction. Doesn't really cause a shift in equilibrium. But activation energy can be used to help explain why endothermic reactions are favored when temperature is increased, just because endothermic reactions, they have a higher activation energy. The higher activation energy with heat, more particles are reaching that activation energy, so they cross. It makes it easier for the reaction. Anyway, okay, the last bits of our Module 5 refresh are this. So calculating equilibrium constant, just remember to have the coefficients as the powers, like the squares, and so you want to make sure that you have products on the top, reactants on the bottom, and put the coefficients up into the corners. You want to make sure that in the square brackets, when you are calculating equilibrium constant, that it's in moles per liter. Doesn't work out if it's not in moles per liter, so make sure you're taking into account the volume. And also just know what K means. So if you have a really high K EQ, if you think about it, that high K EQ is meaning there's a high amount of products in relation to reactants. So we're laying really far on the product side. If it's a low, it'll be greater on the reactant side, so it'd be further on the left. If there are some questions where you haven't really reached equilibrium yet, and it's a question asking whether or not you've reached equilibrium, and this is when you use Q. Q's got the exact same formula as K, but you just sub in the concentrations that you're given. You don't really sub in the equilibrium concentrations, because then it would be at equilibrium. If Q is less than K, then you favor the forward reaction to reach equilibrium because we're too small, we have too many reactants. We want to go a little bit more to the right to reach K. If Q is greater than K, we're too far to the right. We want to move a little bit back to get to K. So we need to shift left, favor reverse reaction. Temperature is the only factor that can change K, like numerically. I said that earlier, but yeah. Last inquiry question for Module 5 is solution equilibria. This is all about solutions. It's KSP. First thing in solution equilibria is the dissolution of ionic compounds and what that looks like on a molecular level with bonds. So ionic compounds, they have ionic bonds. They live in that little lattice structure where the anion and cation alternate because positive and negatives repel each other. Positives and positives repel each other, and negatives repel each other. So they have to alternate positive, negative to be held together. Anyway, yeah. Then you have water, which is what it's dissolving in. These have a bunch of intermolecular forces, hydrogen bonding, dipole forces, and dispersion forces. What happens when you dissolve it is they form ion dipole forces. So the positive hydrogen from the positive hydrogens from water, because water is H2O, the H's are positive, the O is negative. The positive hydrogens are attracted to the anion, and the negative oxygen is attracted to the cation. And those are your ion dipole forces. And the formation of those ion dipole forces, they release enough energy to break the bonds of the ionic lattice, which causes it to dissolve. The other kind of theory thing that you have to be familiar with for solution equilibria is the removal of toxins in cycad fruits. This is through a process called leaching. Leaching just means you have boiling water, you run it through the crushed cycad fruit, and this causes it to go from a solid state inside the little kernels to an aqueous state. If it's running water, or like you put it in a bowl and you constantly change the water, it means it can never reach equilibrium. So you're constantly drawing out the toxins into the aqueous form. Never reaches equilibrium. It just keeps on going until all the toxin is dissolved, and then you can get rid of it. And that's how you remove the toxins. Solubility rules are the other thing that you have to memorize for the HSC. You might not need to memorize it now, but it's a good idea to get used to them. A good way that I remember it, NAGSAG is NAGSAG. NAGSAG is a little thing that I remember to remember what is soluble. So N stands for nitrates, A is for ammonias, G is for group 1, S is for sulfates, A is for acetates, and G is for group 7. For group 7, you have a couple of exceptions. I remember those exceptions as PMS. P is for lead, because lead is Pb. M is for mercury, and S is for silver. And then for sulfates, you also have a few exceptions. I remember it as Castro-Bear. Castro-Bear being calcium, strontium, barium. Those are the main ones that I remember. NAGSAG is just a really easy way to remember the main types of like solids that you'll find or solutions that you'll find. So that's a good thing. And then to the calculation bit, KSP is basically KEQ but for dissociation equation, and it's called a solubility product. That's what SP is for. And for solubility product, you are just multiplying the concentration of the two different ions once a salt has dissolved. And then you account, you put a square if there's two of them. You just account for the balancing as well, just like you would for equilibrium. And you make sure you put the moles per liter in those square brackets. Molar solubility is another thing that comes up a lot in KSP questions, and this just means the moles per liter of a salt that can be dissolved into water. Sometimes you get solubility given in grams per liter or grams per 100 grams or really anything. I've seen kilograms per liter. So you just need to convert it to moles per liter if you want to use it with KSP in any form. To find if a precipitate will form, what you need to do is you need to calculate the solubility and well, don't calculate solubility, sorry. You almost always given like stuff, then you use the solubility and you use the KSP, and you see if Q, which again has the same formula as K, you just see if Q is greater or less than K. If Q is greater than K, that means that a precipitate will form. If Q is less than K, then a precipitate won't form. Cool. So here are a few practice questions. This is just saying which set of conditions would produce the highest yield. We can see there are 2 moles of gas on the left, 1 mole of gas on the right. So to produce the highest yield of phosphogene, which is on the right, we would want a high pressure. And then it is a negative enthalpy change. So negative enthalpy change means the forward reaction is exothermic. Exothermic forward reaction means that we want low temperatures, therefore C. This is just another question. I won't really go through it because I kind of don't have time to, but if I do have time at the end, I'll come back to it. This is what I was talking about with predicting the formation of a precipitate. So we're given concentrations of the ions, so Pb and Cl. So we know that the salt that's dissolving is PbCl2, lead chloride, which means that our KSP would be the concentration of Pb multiplied by the concentration of Cl squared, because there will be 2 Cls. And then you just sub in. So it will be 0.1 times 0.02 squared, and you get a QSP that is greater than KSP, which means that a precipitate will form. So where did I get the KSP from, you might be thinking, to compare with the QSP? That's what your data sheet is for. So your data sheet is like one of your best friends in your exam because it has the periodic table on it. But it also has a list of KSPs, and if the question doesn't say a specific KSP, that means that you're expected to get the KSP from the data sheet. So it's on the very first page, really easy to see, very well labeled. It's got everything you need on there. You just use that. Another good thing about having the KSP on the data sheet is that it kind of gives you a hint as to what is soluble and what is insoluble, because if it's got a KSP, that usually means it's insoluble. It'll form a precipitate. So if you're ever confused if something can form a precipitate or not, look at your KSP on your data sheet, and if it's there, that means it probably will form a precipitate. It probably is insoluble. Cool. And this is calculating the equilibrium concentration. This comes down to algebra. This type of question, you're given the KSP and you need to find the equilibrium concentration. You approach it like an ice table. Approaching it like an ice table, you write your ice table, and then you just fill it in. So it told us that we started off with sodium chloride at this concentration. So the chloride is the common ion, because this is a common ion effect question. Since chloride is your common ion, you put that concentration there, fill out your ice table, and then you sub stuff in. For common ion effect questions, there's a little extra step that you have to make sure that you're not doing quadratic formula. And that's just having a little statement saying that you assume that X is negligible in comparison to the initial concentration of chloride. So then you can cut down that plus X to just being 1 times 10 to the negative 2 instead of 1 times 10 to the negative 2 plus X. And that just makes the calculations easier. and then you just follow along like usual. So that was kind of rushed, but I do need to get through the rest of this lecture. So we gotta move. Let me just see how, whatever. Okay, so we're talking about acids and bases. Properties and acids of acids and bases is the first inquiry question for Module 6. Module 6, the whole thing is about acids and bases, and how it's kind of structured is you start off talking about what is an acid, what is a base, what are the different theories behind it. Then you get to the next inquiry question, which is using Bronsted-Lowry theory, and that's when you just hone in onto one theory about acids and bases and just talk a lot about that, do calculations that relate to that specific theory, and then you use that to do quantitative analysis, which is your titration questions. Now, something to keep in mind for all of Module 6 is, in my opinion, it's very similar to Module 5 in terms of the skills that you have to use. So there's a good amount of theory at the start, like there is in Module 5 with LCP and whatever, but towards the end it gets really calculation based. And for both Module 5 equilibrium questions, where you have the ICE table and all that, both those types of calculations and titration calculations have a massive focus on moles, and moles are so important in getting the correct answer. So if you're not very good at balancing equations, if you're not very good at paying attention to the molar ratios, now is a really good time to get brushing up on that, because Module 6 titration questions almost completely relies on your ability to keep track of your molar ratios. But we'll get to that later. We're starting off strong with simple acids versus bases. So acids, they have a pH under 7. 7 is neutral. Anything under is acidic. The more acidic, the lower. Then you have the sour taste. So if you think of like lemons, they're acidic, they taste sour, and they feel corrosive, which is why you take a lot of safety precautions in the lab when you use high concentrations of acids, because you don't want to get yourself acid burn. For the nomenclature, oh, that's another thing. I just completely skipped that thing in green. They usually contain a hydrogen ion. So a hydrogen ion plus an anion of sorts. Sometimes it's a polyatomic anion, sometimes it's just a normal anion. Yeah. But for hydrohalic acids, which are the ones that you've probably heard of before, like hydrochloric acid, hydrofluoric acid, just like I was saying just then, you have hydro, and then you put the name of the element there. So fluoride becomes fluoric, hydrofluoric, and then you say acid at the end, hydrofluoric acid, hydrochloric acid. And then the formula for that would just be like HF, HCl, HBr. Very simple. For polyatomic ions, it depends on whether it's an 8 ion or an 8 ion. So your 8 ions are probably the ones that you've memorized. So phosphate, carbonate, sulfate, nitrate. They become phosphoric, carbonic, nitric, sulfuric acid. That's what they become. You add ic at the end and then acid. Those are your 8 ions. Your 8 ions, you're probably not as familiar with, but 8 ions are your 8 ions minus 1 oxygen. So nitrite is nitrate minus 1 oxygen. So instead of NO3, it's NO2. So that's how you do a nitrate to nitrite, carbonate to carbonite. And for those, instead of having ite, you add us on the end. So phosphorus acid, nitrous acid. So that's how you name those. Bases, pretty much the opposite of acids. We have a pH that's over 7. We have a bitter taste instead of a sour taste, and they feel a bit slippery, feel a bit caustic. And most of the time they are a cation plus a hydroxide. Now, don't go mistaking this for like all bases have a hydroxide, because that's not the case. You can see in this slide with the nomenclature, there's sodium carbonate and bicarbonate, which they aren't hydroxides, but they're still bases. So don't go thinking that every single base is a metal hydroxide, because it's not. But most of them are. Most of the ones that you'll come across in any sort of HSC question will be hydroxide. So you just name them as you normally would. You just go sodium hydroxide or potassium hydroxide. You just add it on. So bases are really easy to name. Next thing on this inquiry question, like dot point, is indicators. So indicators, as the name suggests, they indicate the pH. It's usually a solution that varies in color, and the different colors can tell us the different pHs. It's often an inorganic acid that's really weak, and this means that they exist at an equilibrium, because weak acids exist at equilibrium. So it means that we just learned about equilibrium, did a little recap, but basically when you add an acid, it will affect one side and cause it to shift to one color specifically, and that color will tell us, oh, it's an acid. Then if you add a base, it'll shift the opposite direction and it will change a different color, and then it will tell us that's a base. So that's how indicators work. If you add an indicator to a solution of unknown pH, it'll usually tell you a range of pHs that it could be in, and that can give some indication as to if it's acidic, basic, what the number of pH is. A common one that you might have used before is litmus paper. You have red litmus paper and you have blue litmus paper. Red is for acid, blue is for base. So you remember that because base and blue not sound the same. They start with the same letter. Base and blue start with the same letter, which means that they go together. So if you have blue litmus paper and you put it in a base, it should not change colors. Whereas if you have red litmus paper and you put it in a base, it should change to blue. Similarly, you have an acid and red. They both end in D, so you know they go together. But if you have red litmus paper and you chuck it into an acid, then it shouldn't change color. It should stay red. But if you have red litmus paper and you chuck it into a base, it should turn blue. Oh, and if you have blue litmus paper and you chuck it into an acid, it should change red. So that's how litmus paper works. Should go the color that it matches. So like acid should turn red, bases should turn blue. Other indicators are ones that you can like drop in and then it will change the color of the solution. Obviously with this type of indicator, there are some positives and some negatives. If you have a solution that's quite opaque or very colored, it can be very difficult to see any color changes in indicators, and it might skew the way you read the pH. But in general, these are really good to test pH. Especially like they're good to test ranges of pH, because if you look, let's look at phenolphthalein, which is the clear to pink one. This is the one you use for titrations most of the time, and it's really fun. It turns a pretty little pink color, but it's clear for so long and then it immediately turns pink. So it's not really a range where you can see exactly what pH it is, because if it's clear, you don't know whether you're at a pH of 1, which is super acidic, or if you're at a pH of like 7, which is neutral. You don't know because all of it looks clear. So that's a kind of downfall of indicators. But the main ones that you'll hear a lot about are methyl orange, bromothymol blue, phenolphthalein, and litmus. Now, if we compare methyl orange, bromothymol blue, and phenolphthalein, what you'll notice is that the change in color, like the massive change in color, so from red to yellow, from yellow to blue, and from clear to pink, those changes in colors happen at different points in the spectrum of pH. So methyl orange, it happens kind of early. It happens before we hit neutral. The change in color happens when it's still acidic. in phenolphthalein, the change in color happens when it's basic. It's far on the right, whereas bromethymol blue, it's right in the middle. So those indicators will be used for different things, different titrations, because different endpoints. But we'll talk about that later because that probably doesn't make sense right now. You can make an indicator from red cabbage. It's a really fun prac. We did it in class. You chop cabbage, you boil it, and then you cool it, and then it's an indicator. How does this work? You can read there. I don't know how it works. Sorry, that was a yawn. I don't really know exactly how it works, but I know the colors. And it's red to yellow. It goes through this really nice spectrum of colors, and it's very similar color spectrum as universal indicator. So universal indicator is a mix of a ton of different indicators to make this one massive rainbow spectrum. We start with red, like a deep red, is super acidic, then green is neutral, and then deep blue is basic. So litmus probably has something to do with it if red is acidic and blue is basic. But yeah, indicators are really interesting. Universal indicator is probably the one to use if you want a specific number of pH, because you can see that like 3 and 4 are yellow, whereas 1 and 2 are red. So you'll be able to tell the strength, like the acids apart, and the bases apart. So that's good. The last kind of thing that you have to do in the first inquiry question of Module 6 are acid reactions. So you should have done this at some point in your chemistry career already, but we talk about it again because it's important. Acids. Acids can react with bases, which are, this is like the main reaction that you need to know for the HSC, neutralization reactions. So you have the acid plus base equals salt, water, and heat. That heat just means that it's an exothermic reaction. Neutralization is always exothermic, so that's why heat is there. Then some examples of that are your standard hydrochloric acid, so HCl, plus sodium hydroxide, which is NaOH, makes water, and then sodium chloride, which is the salt. And then obviously heat, but it's not written there. Cool. Then you've got acid carbonate reactions. Acid carbonate reactions are cool. They form little gas bubbles. And it's just an acid plus carbonate equals salt, water, and carbon dioxide gas. So very similar to a base, but this time we get bubbles of carbon dioxide gas. Then we have acid metal reactions. Acid plus a metal makes salt and hydrogen gas. Same thing, have bubbles from the gas, so that's an indicator of the reaction. But yeah, those are the 3 main acid reactions you need to know. The biggest and most important one, though, is acids plus bases makes salt plus water, and then heat. You just got to know that it's exothermic. And if you know that, you are good to start on titrations. Like if you know how to write out a neutralization reaction, you're probably good to do titrations. But more about neutralization. You actually use neutralization quite regularly. You're just not aware of it. So drinking water is treated to be neutral. From where water comes from, if you think about it, drinking water usually comes from not a plant, but like from a place where it's not going to be pure water straight away. They clean it. They want it to be neutral. They have different chemicals added in so that it's neutralized and then good for drinking. So whenever you drink water from the tap, just know that that's undergone a neutralization reaction. Chemical spills are also a big one. Chemical spills, if we have a massive spill of acid, we don't want that just going out, because like acid is, as we said before, corrosive. You don't want acid just lying around in massive spills where it can be a risk, so you neutralize it. And the main way they do it is with sodium bicarbonate. It's just a powdered substance. You just sprinkle it everywhere and it will neutralize the acid or the base. That's a great thing about sodium bicarbonate, because it's amphiprotic. So if you don't know whether it's an acid or a base that you've spilt, you just chuck on sodium bicarbonate and it will clean up your mess. Even if it's an acid, even if it's a base, it doesn't care because it's amphiprotic. Talk about that more later. And then also like antacids, they neutralize stomach acid to make you feel better in the stomach. That's just how the medicine works. Also with like bee stings, sometimes you put sometimes with different stings there's bases involved, so you put vinegar for the acid because vinegar is acetic acid. There's just a bunch of different ways that neutralization comes in handy in the everyday that we just don't appreciate that much, but neutralization is so important. So start appreciating neutralization. As I said before, neutralization is always exothermic, and that's because when it comes down to the net reaction, it's just H3O plus OH, so hydronium plus hydroxide, makes water. And since that net reaction is really all that's happening in every single neutralization reaction. So since they're all the same, they all have the same enthalpy, which is about negative 57, and therefore it's always exothermic. So there's that. Final thing before we get on to the second inquiry question, which I think is very important, is our good friends Lavoisier, Davy, Arrhenius, and Bronsted-Lowry. These are the 4 theories that you are required to know about acids and bases. Acid-base theory is quite interesting, I think. It's really easy to remember, in my opinion, because I think there's such a natural progression between the different theories. It's like it makes sense, the order, so it's not too hard. But obviously it's still theory, and theory kind of sucks to memorize. But if you understand it, you don't need to memorize it because it's all just embedded in your head. But first theory is Lavoisier. I don't know if I'm saying that correctly. Doesn't matter. But it just showed that lots of non-metal compounds and oxygen, they produce acids when dissolved in water. So carbon dioxide, when dissolved in water, produced an acid. And the hypothesis then was that the oxygen is what's causing the compounds to become acidic in water. Why did this happen? Why did he think that? He just noticed it. But why did we abandon that theory? It's because metal oxides form basic solutions, and it didn't explain why things like hydrochloric acid are acidic when there's no oxygen in it. So we threw Lavoisier out the window. We don't care about that too much. We've moved on to Davy, and Davy showed that Davy hypothesized that acids must contain hydrogen and bases react with acids to form salts. So in Davy's theory, everything that contained hydrogen was basically an acid. And that's why it was limited, because why did so many hydrogen containing compounds, why were they not acidic? Why was water neutral? Why was methane neutral? And that wasn't really explained until Arrhenius. So Arrhenius got it right on, proposing that acidity and alkalinity are due to behavior in water specifically, because that's correct. The way the acids and the bases react with water makes the hydronium and hydroxide, so that's right. And he said that acids dissociate to form hydrogen ions, bases dissociate to form hydroxide ions, And then what happens then is that they can react to form water and a salt. He also proposed that strong acids dissociate to a higher degree than weak acids. This is so correct. That's exactly what determines the strength of an acid. It's the degree of dissociation. So right on there, Arrhenius was probably the closest. And what really limited Arrhenius was that it only talked about behavior in water. So there are acid-base reactions that can happen in gases. There's like tons of different ways that acids and bases can react. It's not just limited to water. So since it only classifies aqueous substances, that's where it was limited. It also didn't explain the pH of salts. More on that later. But that led us to the current theory, I guess. We've had like an extension of this theory to do with electrons, but we don't really care about that as much as Bronsted-Lowry, because Bronsted-Lowry is what is in the syllabus. So an acid is a proton donor. By proton, we mean a hydrogen. So a H+, that is a proton. An acid is a proton donor. It donates a proton. So similar to Arrhenius, where it said it dissociates to form H+, kind of same idea. It donates the H+, which a base, the proton acceptor, accepts. And that's how acids and bases interact. So acid's a proton donor, base is a proton acceptor. How do I remember that? Acid has a D in it. D is the same as donor. D and donor, same thing. So acid is a proton donor, base is a proton acceptor. And it can only donate a proton if the base can accept it. So that's Bronsted-Lowry theory. And I love Bronsted-Lowry theory. I think it's the simplest thing to remember, because you just have to remember that one donates, one accepts, and then you can call it a day. So you have to keep in mind, obviously, like all the other theories that kind of led to that theory in the end, especially Arrhenius with talking about the strength of acids and things like the behavior in water specifically. All of that is still being taken into account in Bronsted-Lowry's theory. It's just they all add on top of each other, if that makes sense. So yeah, I love Bronsted-Lowry theory, and yeah, that's good, because the second inquiry question is all about Bronsted-Lowry theory. So back to Bronsted-Lowry. Which of the following is not a Bronsted-Lowry reaction? For this, you just need to see if someone's donating a proton and if someone's accepting it. So if we look at B, you can see that they kind of just combine. No one really donates or accepts just an H. If we look at A, we see that NH4 donates a proton to NH2, and then they both become ammonia. We see here in C that the H is donated from here to be added on to here, so it becomes H2. And then same kind of idea at the bottom, we have an H from here being donated to here. So B is the only one where none of that's happening. So yeah, you just need to see if there's an H moving around, and that's how you figure out if Bronsted-Lowry is at play. Second inquiry question is using Bronsted-Lowry theory. So Bronsted-Lowry is the proton acceptor, proton donor stuff. That's what you need to keep in mind while we're doing this. First part of the inquiry question is talking about pH and how we measure it. So we've already talked about indicators and litmus paper. You'll have to do a prac in class with measuring pH, but the main way to do it, and do it semi-accurately, or the most accurately that you would get in a school lab, is using a pH probe. pH probes are super cool. You have a lot of things going on with pH probes. You've got really cool curves that you can make. with putting a pH probe in during a neutralization reaction. But yeah, they just spit out a number and tell you the pH, which is always fun. You need to calibrate it, obviously, but you calibrate it using a buffer liquid. But yeah, you just use it to measure pH, which is cool. So that's one of the dot points. Next dot point is all about what is pH, how do we calculate it, all that fun stuff. So what is pH? pH is a measure of hydronium ion concentration. Hydronium ion concentration is water plus a hydrogen, and to me in my head, I know it's not the same, and it's kind of not good to tell you guys this, but in my head, I think of pH as a measurement of hydrogen ion concentration, not hydronium. I know it is hydronium, but the H in pH just tells me it's hydrogen, and I kind of just go with it because they're quite interchangeable. But when you write a reaction and when you write your working out, you have to have it as hydronium. But like, don't be like, where's hydronium from? I've never heard of that before. It's just hydrogen. Like, you don't have to overthink it. It's just hydrogen, but added onto a water. But yeah, it is a scale that's an inverse logarithmic scale, and it means that lower pH, so your super small ones, your like 0.1 pH or 0 pHs, if it can even go down to there, those really low numbers means there's a high amount of hydronium or hydrogen. And that means that it's acidic, because if you remember, hydrogens are your protons, and acids are your proton donors. So if you've got a high amount of hydrogen, that means you've got a high amount of donors. So in the logarithmic scale, because it is a log thing, a change of pH of 1 is a 10-fold increase or decrease in hydronium ion concentration. So that gives you an idea of how severe, not how severe, but how pH works. This is how you calculate pH. It's minus log, and then you put your concentration. You can also calculate pH from POH, which is just minus log hydroxide concentration. But pH and POH, if you add them together, they should equal 14. pH plus POH equals 14. So you can use pH or POH to find the other by minusing from 14. If you want to find the hydronium concentration from pH, what you need to do is do 10 to the minus pH, and then you get the hydronium concentration. Same with POH. If you put 10 to the minus POH, that'll give you the hydroxide concentration, which is sick. And like in the HSC, you're never going to get a question that's just like, here's the hydrogen concentration, what's the pH? Like, they're never going to be that nice to you. Hate to break it to you. They're always going to add a little extra step, something like a dilution or figuring out how many moles it is. So to do that, you need to remember your normal skills. So your normal molar ratio skills, but also C equals N on V. So concentration equals number of moles over volume. And then number of moles equals mass over molar mass. And if you know all of those, you should be good to do the next round of calculations. So here's a bunch of chill calculations. If it says, what is the pH of a solution with a hydrogen concentration of 0.01, what you need to do then is do minus log of 0.01, and then you get your pH, which should be 2. Second question, what is the POH of a solution with an OH of 0.000316? Same thing, you're looking for POH, so minus log of the OH concentration, which is given 0.000316, and you're given a POH of 3.5. Cool. Then what is the pH of a 0.23 moles of HCl? So HCl, hydrochloric acid, is a strong acid, so we can assume that the hydroxide or hydrogen or hydronium concentration is the same as the concentration of the acid. So you go minus log 0.23, and bam, you get a very low one, 0.64. For the pH of 0.1 molar NaOH, sodium hydroxide, same kind of idea. You just chuck in the 0.1 into the minus log to find POH, and then you minus from 14. So minus log 0.1 gives us 1. That's our POH. To find pH, you go 14 minus POH, which is 13. Then for question 5, concentration of nitric acid if the solution has a pH of this much. To find a concentration from a pH, you just go 10 to the negative pH. 10 to the negative 5.73 gives you super small number. But yeah, same thing for the other one. So the really small number for question 5 is like 1.86 times 10 to the negative 6. The very small number for question 6, we're given the pH of a basic solution. So we find the hydrogen, we find the POH first, sorry. So POH will be 14 minus pH, so that's 4. Then we go 10 to the negative 4 to find the hydroxide concentration. Yeah. There we go. So hopefully that's made sense. Some of it probably didn't make sense because I put this slide next door and not beforehand. But you got to know strong acids versus weak acids, strong bases versus weak bases. How you do that is you memorize it. If I'm going to be completely honest, you need to remember which are the common ones. The more you expose yourself to module 6, the more you'll realize which are the strong ones and which are the weak ones. But like right now, you probably haven't really done module 6 yet, so it'll be fine if you don't really know. But what to know is that strength of an acid is associated with the degree to which it ionizes. So more ionization means it's stronger. Strong acids like hydrochloric acid, they ionize completely. So they don't have an equilibrium arrow. They have a full arrow. They go straight from hydrochloric acid, and all of that hydrogen in the hydrochloric acid becomes hydronium. For weak acids, they do not ionize completely. So they exist at this equilibrium, and we need something called a Ka to figure out the exact hydrogen concentration or hydronium concentration. So same kind of thing with bases as well. But if you compare equal concentrations of strong acids and weak acids, you'll notice that the strong acid has a lower pH because it has more hydroniums because it had more hydrogen ionizing. If it has more hydronium, has a higher concentration, lower pH, more acidic. So usually strong acids have a lower pH, and then weak acids are the ones that end up being buffers and have a mid-ish pH. Common strong acids and base. Oh, and I forgot to say that also applies for bases. Strong bases dissociate completely. Weak bases exist in equilibrium, just like the acids. But yeah, so strong acids and strong bases. Here's a list. Your group 1 hydroxides, they are your strong bases. Your strong acids are, there's not really a pattern to it. It's kind of just like the common ones. So hydrochloric acid, nitric, sulfuric, phosphoric. Sorry, there was a truck just passing my house. Phosphoric acid, hydrobromic acid. Those are your strong ones. Have to remember those. And then you've got weak acids, which are usually your organic ones. Carbonic acid as well. Yeah, and then weak bases common, like the most common weak base ever would be ammonia. But like, to be honest, there's not really a fun little pattern to remember this like there is with solubility rules and like NAG-SAG. For this, honestly, it's just remembering it, which is such a trek. But the more you expose yourself to questions, the more you study hard, the easier it is to remember. Cool. Okay, so the action of acids and bases in water, this is something you need to consider when like drawing out any dissociation equations for acids and bases. But in water, what happens is the acid donates its proton to the water. So it becomes an anion plus hydronium. So the acid donates it to the base, which in this case is water. For bases, you have a base, which is just like that B, and it takes a proton from the water because it's a proton acceptor. So that's how it becomes BH plus OH minus. So yeah, back to Bronson-Lowry theory, it's just about which one donates, which one accepts. Water acts as the acid when it acts with a base in water. Water acts as the acid because it donates its proton to the base, which accepts it. We have some other terminology that we have to get used to, which is conjugate acids and bases. So if you have a base plus an acid, the base, after accepting the proton, so let's say the base is the water, once it's become hydronium, the water has acted as a base because it's accepted a proton. Once it's accepted it, it's no longer a base, it's a conjugate acid. Once the acid has donated its proton, it's no longer an acid, it's a conjugate base. Same kind of thing, when a base is just as its own, it's fine. Once it's accepted a proton, it becomes a conjugate acid. Once an acid, which in this, like the second case here, that one, the acid acting in this situation is water. Once that has once that has donated a proton, once it's donated a proton, it has become the conjugate base. Now, the strength of conjugates is something else completely. So the strength of conjugates is kind of an inverse relationship. So if it's a strong acid, like let's say hydrochloric acid, its base, its conjugate base, so just chloride ion, that conjugate base is weak compared to the acid. And yeah, if it's a weak acid, it's also a weak conjugate base. But yeah, if it's a strong acid, it has a really weak conjugate base. It's just how it works. So that's the strength of conjugates. Now, I did say a while ago that I'd get back to salts. And salts, you can have acidic and you can have basic salts. You can also have neutral salts. But the way to figure this out, there's like a lot of text on this slide, but really there's a really easy way to figure out if a salt is acidic, basic, or neutral, and it's to figure out what made it. So let's say we have sodium sulfate. Sodium sulfate is the salt. You think of what was the acid, it would have been sulfuric acid. What was the base? Probably sodium hydroxide. So we have our acid, we have our base. We need to figure out if it's strong base or weak base. Both of them are strong. Sulfuric acid is a strong acid, sodium hydroxide is a strong base. So since they're both strong, it becomes neutral salt. Now, if we have, let's say, acetic acid with sodium hydroxide, so we end up with sodium acetate as our salt. Acetic acid is a weak acid, but sodium hydroxide is a strong base. So it ends up being a basic salt because the strong base kind of overpowers the weak acid, and then it goes too far and it becomes a basic salt. You can also think of it in terms of the conjugate acids and bases, but I just find that hard to wrap my head around. So personally, I just go for the what made it kind of deal. But we'll talk through the other one. So if the conjugate base, if you have a conjugate base of a weak acid, it'll form a basic solution because it can act as a weak base. And if you have a conjugate acid of a weak base, then it can produce an acidic solution. But again, just figure out what made the salt. Use the two ions to figure out what made the salt, and then figure out if those were strong or weak. And if they're both strong, you're neutral. If they're both weak, you're neutral. If you have a strong acid and a weak base, so like hydrochloric acid and ammonia, strong acid, weak base means an acidic salt. Strong base, weak acid means a basic salt. Like this. I chose great examples. I completely forgot making this slides. So I didn't realize I'd use the exact examples, but fun time. Strong acid, weak base means acidic solution, which is what's going on here. Cool. So final kind of thing for this dot point are your protic things. I think that's just a funny name for the slide, but your protic things are, oh no, this is not the last thing we have to do for the next one. Kind of. Sorry, I'm just like looking ahead. So your protic things. You've got your polyprotic, which means you can donate multiple stuff. So for example, monoprotic is like hydrochloric acid. You donate one proton, whereas diprotic, you have 2 protons that you can give out. So just like sulfuric acid. Then phosphoric acid has 3. It's triprotic. You can give out 3 whole protons. That's what polyprotic means. Amphiprotic means that you can donate or accept. So this is what I was talking about with sodium hydrogen carbonate. It can act as a a proton acceptor or a proton donor. So if we have the ion bicarbonate is what is amphiprotic. So we have a bicarbonate ion and it's added to hydronium, which represents the acid. That hydronium is the acid, so it donates a proton. So then it makes carbonic acid plus water. And then if it's a base, sorry, that was a fly. If there was a base, you have I forgot the word. You have bicarbonate ion plus hydroxide. The bicarbonate then acts as an acid, donates its proton to the base to make water and carbonate ion. Okay. Other thing, strength, we've already talked about, the degree of ionization. Concentration is something that you should already know. It just refers to how much is, like, how many molecules in that volume. If it's super concentrated, that means that you've got a lot of particles of the acid in there. If it's not concentrated, you don't have a lot going on. These are really good diagrams because it shows strength and concentration. You can see the strong concentrated, all the particles have separated and there's lots of them, whereas strong dilute, there's not many of them, but they're all still separated. Weak dilute, there are some that are still together, some that are separated, which shows that degree of ionization. And weak concentrated, same degree of ionization, there's just more particles. So it's a really good representation of strength versus concentration. Now, a trickier calculation that you might have to do is calculating the pH of resultant solutions. And for this, you've got to work out the limiting reagent. So in my personal experience, I've just hated limiting reagents. I understood it towards the end of year 11 chemistry, but I just never understood it while I was doing it. And I feel like that's a kind of a common theme with chemistry. You kind of just don't understand limiting reagents until you finally like have a click moment and you're like, oh yeah, limiting reagents makes so much sense. Yeah, so if you're not cool with limiting reagents, maybe brush up on that before trying module 6. But for limiting reagents, what you do is you figure out the concentration of, like, you figure out the number of moles of hydrogen and the number of moles of hydroxide. Whichever has the least amount of moles, that's your limiting reagent. Once you find the limiting reagent, that's all that's going to react. So you find out what's left over of the other one. And whatever is left over of the other thing, the non-limiting reagent, since it's mixing acids and bases, so since neutralization would have occurred, the pH would be neutral. So the only thing that's affecting pH would be the leftover once you've reacted all of the limiting reagent. So you use the leftover to calculate pH. You also have to take into account changes in volume. So if you're adding 150 milliliters of one thing to 150 milliliters of the other thing, you no longer have a concentration that you originally had, because now you have a different volume. So you usually end up with a lower concentration because you have a changed volume that's bigger. So remember that, because that's something really easy to forget. And yeah, don't really worry too much about weak acids, because there's the extra step of Ka that you'll need to do, and that's kind of a pain to put in with the rest of the stuff. But yeah, convert moles into concentration, then find pH. So it says 250 mils of nitric acid at this concentration is diluted to 500 and of KOH, a strong base. What is the resulting pH? Cool. So what you do here is you write out your equation first of all. You have nitric acid plus potassium hydroxide makes potassium nitrate and water. Then you need to figure out the number of moles of each. So you start off with the acid, which is 0.25 liters, because concentration is moles per liter, multiplied by 0.33, and then you find the number of moles of the base. Then what happens is that you see that the limiting reagent is the base, which only has 0.05 moles. You have 0.05 moles being used up, so you take that away from the 0.825 of the acid, and you end up with 0.0325 moles of acid after neutralization occurs. So that's what we'll be using to find the pH. That's the number of moles. We need to find the concentration before we can put it into our pH calculation. You have it in moles. We want it in moles per liter. So C equals N on V. We put moles on the top, so 0.0325 goes on the top, and V goes at the bottom. Your volume will be 500 plus 250. It'll be 750 mils, because you are adding them together. It becomes new volume. So it'll be 0.75 because we want it in liters, and that'll give us 0.043 moles per liter. Then that 0.043 can go straight into our minus log, and that'll give us a pH of 1.36. Now, the hardest step in that was accounting for the change in volume. Everything else is stuff that, if you are really good with your moles, you wouldn't have too much trouble with, because it's just a 1-to-1 ratio, so finding the limiting reagent is quite simple. You just go which one was limited, which one had less amount of moles. But if it changed the molar ratio to, like, let's say it was with sulfuric acid instead of nitric acid, it'll be 1 sulfuric acid for 2 of the potassium hydroxide. So that change in molar ratio would have changed how we did the limiting reagent, which would have made it a little bit trickier. But yeah. This is a simple multiple choice question. Which beaker contains a strong acid? You pick whichever has ore dissociation, and then you pick which one is concentrated. So B is our answer because all of it's dissociated, and there's more particles in it than B, which is also ore dissociated. Then this one says which is the conjugate base of the dihydrogen phosphate ion. So it's asking which is the conjugate base, which means that that dihydrogen phosphate must be working as an acid. So it donates a proton. We look at what is the dihydrogen phosphate minus a proton. It's HPO4. So that's the conjugate base. Now on to the fun stuff. I'm trying not to run out of time. I think we'll be fine, but yeah, let's hope for the best. So quantitative analysis is probably my favorite part of Module 6. I love a good titration question. I think they are really easy marks to get because they're worth so many marks. But if you're good at moles and you are good at kind of workshopping around different weirdly worded questions, these can be really good. So what is titration? There are lots of funny like TikToks about it because it's such a common prac and it's about like toning it pink. There's lots of media on titration because it's so funny. The prac, like when you do the prac, it's actually so fun. The stress of getting the perfect endpoint is something that's really, it's an experience. So have fun doing that prac. But the deepest, corest part of titration is you're trying to find an unknown concentration. And you use neutralization to get there. In this, we assume that the endpoint is the equivalence point. It's not in real life. It's not like that, but we just pretend that the endpoint equals the equivalence point just because it's really hard to get a precise change. And then yeah, we use moles and stoichiometry to figure out the concentration of an unknown solution. So moles are really important, molar ratios are really important, and even down to like indicator choice can make all the difference in a titration. But the objective, finding an unknown solution's concentration. What we need to do this is a standard solution. Standard solutions are accurately known concentrations. We know the concentration because we've made it up. We've made it ourselves. It's very easy to standardize, like to figure out the concentration of a substance if we have a good standard solution. And a primary standard is what we do when we make a standard solution. It's when you have to actually dissolve a substance by measuring the mass and all that stuff. The criteria for a good standard solution, a good primary standard solution, is it has to be stable and pure, and it can't absorb water. It has to be hydrophobic, because if it absorbs water, that'll change the mass over time, and that will lead to incorrect calculations of the concentration. And it has to be a reasonably high molar mass. The reason for this is if you have a high molar mass, it prevents small changes in mass, like you're losing a little bit of mass. That won't make a big difference on the number of moles because it's such a high molar mass. It'll be such a tiny fraction of a change. If you have got a really low molar mass, your half a gram being lost on the scale turns into a really big percentage. So you want a high molar mass. And you want an accurately known chemical formula. Sodium hydrogen carbonate is a chill one, very easy to use. I like that one. I don't know how good of a standard it is, but yeah, we used that one time. And how to prepare it, for a primary solution, you need to calculate the amount of solid by finding the mass from the molar mass, and then you want to measure it on an electronic scale. Then you want to dissolve that solid in a small beaker, then change it into a volumetric flask. You want to make sure that you're not losing any of the solution in the beaker. You want to make sure that you're cleaning it out, flushing it out with distilled water so that all of the dissolved bits can get out and you're not leaving anything behind. And then you fill the volumetric flask to the calibration line and then add it until the meniscus is just at the line. It's important that you don't just go filling it up and like approximating it at the calibration line. You want to go drop by drop at the end because you want it to be exactly right. Then you insert the stopper and you do inversions. Usually do like 5 inversions, and then you're good to go. Now, for the actual titration, you'll be very familiar with this procedure by the end of the module, just because you're going to do it so many times, because it's all about accuracy, and when it comes to like reliability, you want to have lots and lots of attempts at it, I guess. So for the procedure, you need to make sure everything is rinsed with the correct liquid. Now, the correct rinsing is a very important part of titration, and they get so upset when you rinse wrong. So to prepare a pipette, you need to rinse with water, and then you need to rinse with the solution that you will be pipetting. You can't just rinse it with water, because then it will change the concentration if there are water droplets still stuck. Then you need to rinse the burette, and you rinse it with water and then the solution that's going to fill the burette. Then you rinse the volumetric flask with just distilled water, and then you rinse the conical flask with just distilled water. So pipette and burette have the extra step of rinsing with water and then with whatever's going in there. Everything else, just distilled water. Don't go rinsing your conical flask with acid or your volumetric flask with acid. It's just not going to work out well. If you rinse incorrectly, you might change concentrations. You might have an endpoint happening earlier than expected. It'll screw all your calculations. So do the rinsing correctly. But once you rinse, what you need to do is you need to use the pipette to measure the solution that you want to put in the conical flask. Put it in there, and then you use your indicator of choice. Choosing an indicator depends on what you're titrating. So for like a weak acid, strong base, you want phenolphthalein. Anything that has a changing point around 7, you want bromothymol blue. And anything that has a little change happening in the acidic region, you want methyl orange. Phenolphthalein is the main one that we use. It's the famous one. It's the pretty pink one. Most of the time you're going to be using that. So you put a couple of drops of the indicator into the conical flask, and then you need to fill the burette, the one that's being held by the stand. You fill that burette with titrant, whatever you're titrating. Then you do a rough titration. You just add the second solution from the burette into the conical flask, and you want to make sure that you're swirling the conical flask, because especially with phenolphthalein, like it might look like a drop of pink and you're like, oh my goodness, I've hit the end point, but then once you swirl it, it will go back to being clear. So you need to keep going until the entire thing is pink. But yeah, you want to just keep swirling until the indicator changes color. Then once it's changed color, you repeat it all over again until you have 3 readings that are really close with each other, between 0.05 mils of each other. So when you get to the end of your titration, you don't want to be like opening the tap of the burette and letting everything out. You want to go drop by drop, literally drop by drop, and collecting those drops so slowly. So you need really careful hands for it. And then you perform calculations. So for calculations, these are so much more fun than the theory of titration, in my opinion. I love a good titration calculation question. How we do it is it tells you the endpoint is reached at a certain concentration. At a certain volume, and you're given the concentration of the acetic acid. So it says that you have 25 mils of acetic acid. You can use that 25 mils to find the number of moles of acetic acid because you had the standardized concentration. But above all, the first thing that you need to do is write out your equation. So NaOH plus acetic acid makes sodium acetate plus H2O. Then you use C equals N on V, rearrange it so you can find N. to find the number of moles of acetic acid. Then the 1-to-1 ratio of sodium hydroxide and acetic acid means that the same number of moles was used up in the neutralization reaction. So we just put that same number of moles over the volume, C equals N on V. And the volume that they gave us for the titration was 19.3. So that's the volume that goes on the bottom. And that gives you the concentration of sodium hydroxide. Same kind of thing here. They analyzed aspirin tablets for quality control. They had 25 ml samples of a 0.1034 solution titrated against sodium hydroxide. Average volume was that. So same thing, it has a 1-to-1 ratio. So we use the concentration of standardized hydrochloric acid. So we go N equals C times V, 0.1034 multiplied by 25 mils. And then we find the number of moles, and that mole is the exact same amount as the number of moles of NaOH because it's a 1-to-1 ratio. So then you just divide by the average volume required for neutralization, which will give you that, and that's your concentration. Yeah, so it's actually quite simple. It comes down to the molar ratios. We're gonna skip that question because we're gonna run out of time. But now we're gonna talk about titration curves. So titration curves, I briefly mentioned them when we talked about pH probes. But when you got a pH probe, you can stick it in, do a neutralization, and it should come up with a curve that looks like this. The curve changes shape depending on whether it's a strong acid or base, or weak acid or base that you're dealing with. The equivalence point is when neutralization has occurred. And that equivalence point changes location based on the reactants. So if we look at the first one, the strong acid, strong base, equivalence point happens at a pH of about 7, which checks out because strong acid, strong base. And then it looks pretty, it ends at a pretty high base, a pretty high pH, and it starts at a pretty low pH. So that's how we know that it's strong acid, strong base. If we look at our weak acid and weak base, we have this kind of shape where since it's weak and weak, it still occurs at a pH of 7, but the volume that it occurs at, not the volume, the base pH that it gets to is much lower. The most interesting shape, I think, is the weak acid, strong base, because it has this buffer period here. So it's not the same smooth kind of shape as these guys, where it's gone denting low like that. It's got this buffer period, and that's because it's an acid. It's a weak acid. It exists at equilibrium. That's showing how it exists at equilibrium. And then equivalence point, blah, 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 blah. And yeah, same kind of thing here. Strong acid, weak base. Got a weird thing going on. Same kind of shape as this one, but yeah, it has a lower resulting thing. Yep, cool. Equivalence point changes based on the different things. So the equivalence point for these graphs are a little bit whack. But for strong acid, weak base, you should have an equivalence point that's closer to the acid side. So the equivalence point should be happening lower. And then for strong base, weak acid, the equivalence point should be happening higher up. So it should be happening like 8, 9 pH, over 7. So yeah, that's that. Another type of graph that you might see that you have to interpret for titration are your conductivity graphs. So this is the same kind of thing, but for electrical conductivity, and it's based on the ions that are present. So the most prominent looking V, that's for your strong acid, strong base, and that's because you start off with lots of conductance because you've got a strong acid or strong base, it's dissociated completely, lots of free-floating ions. Then, as they start to react, it starts to form water, which isn't reacted. It's not like it's not conductive. It's not an ion, so that's not being measured. So the number of ions decreases and decreases as more start to come water. Then, when you get to the point at the bottom, that's when all of it has reacted, everything has been equal. Now, the upwards slope is just adding excess in. So let's say we keep on adding a base to it. There's no more acid to react with. So it's not neutralizing it, or now it's just accumulating more ions, and that's why it goes back up. So that's how you explain strong acid, strong base graphs. For weak acid, weak base, the most interesting part is the plateau at the top. This is specifically for ammonia, because ammonia isn't like an ion that's charged. Once you've added excess ammonia, it's not going to change in conductance, which is why it plateaus. And same kind of idea for the plateau in the strong acid, weak base one. But yeah, I think that's a pretty good overview of conductivity graphs. Now we talk about Ka and pKa. This is a very good opportunity for the worlds to collide between Module 5 and Module 6. So Module 5 was about equilibrium, and you deal with KEQ, KSP, and you can easily mix that kind of theory with Ka, because it's about the degree of dissociation. So if you look at Ka, it's the concentration of hydrogen, concentration of the ion over the concentration of the acid. So it's basically KEQ, but for acid dissociation. And this just tells us the degree of ionization. A high K means that you have a really strong acid, and a low K means that you have a weak acid, like carbonic acid. There. Basically, if you have Ka, you are able to find out the hydrogen concentration of weak acids and then find out their pH. Because unlike strong acids, where you can just say the concentration of the acid is the concentration of the hydronium, you can't do that for weak acids because it doesn't dissociate completely, which is where you use Ka. So that's how you use Ka, yeah. pKa is like what the same formula as pH, but instead of putting hydrogen concentration or hydronium concentration, you put your Ka there. And this again just shows the degree of ionization. So if you have a low pKa, it means it's a strong acid. Low pKa is a strong acid. High pKa is a weak acid. And this just tells us all we need to know about strength. And this is what we use to figure out the concentration of hydrogen ions for those questions about pH for weak acids. So if we have a question like this, the pH of a propanoic acid solution was measured to be 2.7. The dissociation of propanoic acid is represented below. Calculate the Ka. So first thing to do is write a Ka expression, which will be hydronium on the top multiplied by, sorry, that was really loud. I dropped something. Multiplied by the CH3, CH2, blah, 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 blah. Those two multiplied together on the top over propanoic acid concentration on the bottom. So 0.3 is what's going to go on the bottom, because that's our concentration of propanoic acid. Then we need to find the concentration of hydronium and the other thing. These two, we need to find this concentration, and that's where we use the pH. So we find hydronium concentration by doing 10 to the negative pH. So 10 to the negative 2.7 will give us this concentration, and it's a 1-to-1 ratio, so they'll be the same. So it'll be the two same things on the top over 0.3 minus that number on the bottom. Why does it minus that number? It's because it's like an ice table. So really you should draw an ice table, because I low-key forgot about that step just then, and it's really easy to forget about that step. So it's a good idea to draw an ice table underneath. Your initial for this would be 0.3, and then the change will be minus x, and that will make it easier. But yeah, that's how you do that. There are different ways to analyze acids and bases. It really depends on the industry, culture, bunch of things. Main way to do it is using digital probes, like pH probes, to give a digital reading. You can also use it to measure conductivity. There are also some automatic titrators, which can make it more accurate and reliable. Acidity or base or alkalinity can be measured in like a bunch of different industries, food industries, water facilities for making drinkable water, weather, and also with the fruit toxicity removal. All that stuff comes together to use our knowledge of acids and bases for something in society. So like ant stings and blue bottle stings with plant saps, or different acids and bases. That's a way to use acids and bases in society. So that's something like in the syllabus, it's not something you have to write about particularly. It's just something that they want you to appreciate. They want you to understand that they're not only talking about acids and bases because they don't know what else to put in the syllabus. They're talking about acids and bases because it is so present in our society. And that makes them, yeah, they just love to talk about relevant stuff. Chill. Okay. So, some final things. Buffers. Buffers are, if you, I'm a biology kid. I loved biology in high school and I still study biology. So buffers are the most interesting thing in chemistry to me because there are so many natural buffers in like ecosystems and also in our body, like the bicarbonate buffer system in our blood. But a buffer is a weak acid and its conjugate base. And this just means that it can resist changes in pH because since it exists at equilibrium with the weak acid and conjugate base, it can act as it can buffer at additions of both hydronium and hydroxide to act as an acid and a base so that the pH remains constant. And yeah, this just means that you're able to buffer these changes in pH. It has to be a weak acid or else it doesn't work. If we look at the acetic acid acetate buffer system, which is the one that I did in class, if you have an acid, the hydronium is acting as the acid, right? So it donates that hydrogen to the acetate ion, and that's the conjugate base. So it donates hydrogen to conjugate base, which will mean that you don't get much change in the pH. If you add a base, you add OH, it needs to accept a hydrogen. So the acid, the acetic acid, will donate its proton to the OH to make water. And that will, again, stop a change happening to the pH because it's counteracted it. So that's pretty cool. There's a bunch of natural buffers in living systems like aquatic environments, blood. I love the bicarbonate buffer system in the blood. It's so interesting. I did exercise science this year, exercise physiology. So there was a lot of talk about the bicarbonate buffer system because it's really important in stopping us from going into a state where our blood is too acidic for us to function and then we die, especially when we do stuff like exercise because we've got a lot of carbon dioxide forming then. But they're necessary to keep the correct pH because pH is it's like the environment. Like it's like keeping the correct temperature for your body. You need to keep the correct pH for everything in your body to function. That means enzymes. That means different cell structures. Everything needs to work at an optimal pH. So it's a really narrow window that we're working in, which is why we need buffers to make sure that we're never going outside that window where it might be dangerous. And for like the blood buffer system, the window is like 7.35 to 7.45 pH. So we've got tiny room to work with. So it's really important that we have a buffer system there because we want to make sure that we're buffering properly. So yeah, love natural buffers. Yeah, so there's the dihydrogen phosphate and hydrogen phosphate system in the fluids of cells to keep pH constant in the cells. And same kind of idea here with the dihydrogen phosphate. It acts as a proton donor. So whenever a base is added, that donates a proton. And yeah, for the hydrogen phosphate, that acts as the proton acceptor. So whenever an acid is added, it accepts the proton that's donated by the acid. And that's how natural buffer systems work. So, some final practice questions before I go into either overtime or talking too much about my general HSC advice. Chlorous acid, HClO2, has a pKa of 1.96. Nitrous acid has a pKa of 3.39. And then it asks what of the following solutions has highest pH. So the lower pKa means that there is lower pKa means that it's a stronger acid, which means that stronger acid, which means that you have a higher degree of association, which means that usually you have a higher pH. So why is it not chlorous acid? Well, this is because of the conjugate acid conjugate base situation. pKa is weak. pKa of 3.39 indicates a weak acid, which means that it would have a strong conjugate. And that conjugate would be there. Cool. Here is another HSC practice question. It says that you have these two different graphs and then explain the differences in terms of relative strengths and concentrations. So we can see that acid 2 has the buffer region right here, which means that it is weak compared to acid 1. In terms of the concentrations, you need to look then at how much volume was required. So both were monoprotic, which means both were at a 1-to-1 ratio with KOH. Acid 2 took up way more volume in order to reach the equivalence point, which means that it had a lot more molecules to deal with. So acid 2 is more concentrated, and that's what you have to do. So yeah, acid 1 is stronger because there's no buffer region and the equivalence point is at 7. Acid 2, it just took more base to neutralize it, which means it's more concentrated. So a little summary. For the key skills in Module 6, we have titration calculations, which is all about your molar ratios. If you've got nothing going on for you in titration calculations, at least write something down about the ratio of the moles. So write a balanced equation, then state the molar ratio of the acid and the base, and that'll definitely get you marks. And then titration curves, you need to know the pH ones, which are the curvy ones, and then the conductivity ones, which is like the V-shaped one. pH calculations for mixed or diluted solutions are another skill, and then you have your Ka and pKa questions. They come up really, really regularly when you mix Module 5 and Module 6 together, just because like Module 5 is all about K, and this is a way to cross them over. So when you get the multi-module questions, Ka and pKa will probably come up. But some extra reminders are, don't forget to learn the theory parts of the syllabus. Don't forget to learn about the everyday neutralization reactions, the different theories that have shaped the way we understand acids and bases. So your Lavoisier, your Davy, your Arrhenius, and of course Bronsted-Lowry. So Don't forget those theory parts. And that goes for Module 5 as well. I know we did a refresh for Module 5 at the start. I don't really have a summary of Module 5 little slide, but I will say there is a lot of theory in Module 5, especially about like solution equilibria. Most people dive straight into the calculations without doing any of the theory on the removal of toxins from the cycad fruit and the actual like what happens when we have salts dissolving, what are the bond changes. All of that theory is worth knowing because as much as the HSC is going closer and closer to being more calculation based with HSC, like every year there's more calculations. Even though that's happening, the theory is still in the syllabus, which means it's equally as likely to come up as something that you need to deal with. So don't forget that. Now it's time for the fun stuff. I think that the HSC it's kind of a weird situation, but especially since when you're watching this, it will be January. You've kind of been living in a HSC situation where you're like not year 11, but you're not year 12. You're doing your HSC subjects with the HSC syllabus, but you're not really year 12 yet. And you're starting to go into the year when you're actually year 12. And that is super, super scary. Especially because now it'll start to feel like everything is counting towards something. And you no longer have the mindset that I had in term 4 of year 11, the first term of my HSC syllabus, where I was just like, it's okay, I can make it up next year. Like, it's scary and it's stressful. So I thought I'd give some unsolicited HSC advice, which I do at the end of all of my lectures. If you've made it this far, some people might have tuned out. I don't really know. But first thing I'll say is burnout is so real. And I felt it. My friends felt it. And did it make high school a little bit annoying at the end of the year? Yes, but I managed to get around it. I never let myself get so burnt out that I ruined my entire senior year experience. Yeah, so make some memories. Do stuff that you enjoy. Don't drop all your extracurriculars, because one thing I was super glad that I did was I kept almost all of my extracurriculars in year 12. And even though I was stressed sometimes, all my extracurriculars contributed to me being less stressed. I went to dance, I went to piano playing. It was so much fun to have those extra things to do to give myself study breaks where I felt productive, not on the HSC stuff, but I felt productive in my own way, and it was just fun. So make sure you take time to do stuff that you enjoy. Another tip is plan something cool to do once the HSC is over. I went on a trip with my friends, and that was really fun. You should try do something like that too, and find your way to de-stress. I liked to go on runs. I liked to play Just Dance. Those were my ways to de-stress, and I found them really useful. So if you are ever in the mood to de-stress, maybe go on a run. I had a nice little track that I would go on every day. Not every day, most days. And that was a great way of me to forget everything that was going on in the HSC and just focus on myself or whatever. But yeah, if uni is stressing you out, know that there are so many pathways. I know people who have started a degree because they didn't know what to do and then just changed and changed and changed. I know people that aren't going to uni. I know people that they don't know if they're going to get in and they're really stressed, but I was just like, that's fine. You can come again the year after. There's so many pathways, so don't stress out too much about that. Work together. HSC is a team effort. Learn your study methods. Do the study methods that are suited for you. If you hate working with other people, then maybe don't work together. Do active recall. That's like my biggest tip. Maybe not for chemistry. Chemistry, my biggest tip is to do practice questions, and as many practice questions as you can. But active recall is also good for the theory stuff. Things like flashcards, blurting, all of that will be so much more effective than any note taking. Go to sleep. have some rest. I don't know why I feel like I'm qualified to say that, because I stayed up until 3 last night reading a book. But yeah, go to sleep, chill out, take a nap. Um, yeah, it's not that deep. You don't need to lose sleep over the HSC. And sleep just makes your performance better. Like, that's a given studied fact. And you'll probably encounter a couple of rough bumps in your HSC. Just know that there's nothing you can do about it. Giving some tough love here, but if you get a bad mark, you can't go back and change it. You can't resit the paper. You just have to go, oh, why did this happen? How can I make sure it doesn't happen next time? And then take proper moves in ensuring that it doesn't happen again. And then you can change your next results. You can't change your past ones, but you can change your next ones. So, thank you all for coming. I hope you guys learned something today. If you didn't learn anything, then I'm so sorry. Hopefully someone in the live chat was helping you out if you were really confused. And yeah, I hope you come back for another lecture. Who knows if I'll still be taking the lectures by the next lecture round. But I'm glad you've come. I'm glad you've stayed to the end. And I hope you have a wonderful afternoon, day. I don't really know what time you're watching this. But hopefully whoever's in the live chat has been answering your questions. And if you have any more questions, I'm sure they can be answered by some type of resource that we have at ATAR Notes. But yeah, thank you so much for watching. I hope you learned something. I hope you enjoy Module 6 as much as I enjoyed Module 6. I hope you have fun doing titration practice. And I will see you next lecture, maybe. Bye! This is